Good morning, good afternoon, everyone. You stuck through second week of class of numerical methods. Thank you so much. Apparently, I have to exit full screen out of this one. Okay. Your exam 0 is going to be this Thursday. You have a study guide and an sample exam on the front page of Canvas. This exam is on prerequisites, and it will be on Thursday here in class, 20 minutes long. You're allowed a single double-sided letter-sized note sheet, otherwise closed books, closed notes, etc. It should be fairly easy. In all the years I taught the class, exam 0 was a free 5% or whatever the percentage ends up being, 7%. So make sure you grab that opportunity and put it on record, okay? I'd like you to put your names in front of you and reassemble with your assigned groups or your self-assigned groups, okay? And I'm hoping now you have group names. If you don't have a group name, come up with one right now. You can change it later. It's okay. And I'll be calling on the group name, okay, when we are discussing ideas. Do you have a question? Name tag, name and group, okay? Okay, let's have some group names, please. I'll be calling on the group to participate in discussion. Pardon me?
Do you need to have something that says the group name?
Yes, please. Or if you want, I'll just call, it's hard, I'll just call someone, right? And then you'll say, oh, we are group. So that would be nice. If you have a group name, put it on a tag, please, and put it in front of you. This way, I'll just call on the group name. You two are in your own group. Have you come up with a group name yet? So F of X.
Purple flying dinosaurs.
Purple flying dinosaurs. Okay. Now that the names are behind us, today's lecture is going to be a fun lecture. We're going to start doing some serious programming. Okay? We're going to start doing some, hopefully, a couple of for loops or a while loop. And we'll also be looking at quick indexing in a NumPy array, just to show you the power of that. However, that has to be done in context, and we're going to do it in the context of the approximate error. Last time, we talked about the definition of an error. And we said it's the difference between two things, an approximation, in our case, because we're dealing with approximations, and some other value. We started by defining the true error, where we said in an idealized situation, you know the true answer. You come up with an approximation that represents that system for which you know the true answer. The example we did last time was a derivative. And we took the difference between the approximation and the true value. We called that the true error. Correct? And if you divide by the true value, we call that the relative true error, because that gives you a sense of how big the error is. Remember the example of the bridge? A 1 meter error committed in a 1,000-meter bridge, measuring a 1,000-meter bridge, is insignificant compared to a 1 meter error committed in measuring a 10-meter wall. Okay? Then we argued that, well, the concept of the true error is really not helpful because we don't know the true value. If we knew the true value, we wouldn't need to do an approximation in the first place. And then we argued why, under what conditions the true value is useful, when what we called verification. So you're setting up a Python routine. You want to make sure it runs, okay? and it's computing some systems that you've never solved before, okay, or for which you don't have a true answer. You don't know the answer, right? So you go and test your Python routine on a simplified system or a simplified equation, simplified model for which you know the true answer, just to make sure you got it right, okay? So that process called verification, that's where the true error or the true value is useful. However, in reality, we do not know the true value, okay? Again, otherwise we wouldn't need an approximation. Hence the concept of the approximate error. Now don't confuse that with approximation error. Everything we're doing here is pretty much an approximation to a true system, okay? However, the error committed in applying the approximation, we're going to measure it, we're going to approximate that error, and we're going to call that approximate error. I went over the definition quickly last time, and I said the approximate error is defined as the difference between a current approximation and a previous approximation. And that kind of is not very clear initially, but you will notice as we study numerical methods, we deal with iterative processes. We start with an answer or a guess, and then we keep adding to it or subtracting from it. We keep changing it to improve it. And every time we make a change to the initial guess, that's a newer approximation that we're making, and we're hoping, for the most cases, that these approximations are better than the previous ones. In other words, what I mean by a current approximation is a slightly better approximation than a slightly worse approximation. Okay, we'll do examples. It will fix that idea in your mind. Clearly, the current approximation, what I mean here, is one that is a little bit more accurate, or has more terms in it, or just a little more accurate. Alternatively, you can just define the approximate error as the difference between a more accurate approximation and a less accurate approximation. Again, those are the same definition. So however you define this, whether you say current minus previous or more accurate minus less accurate, they both mean the same thing, okay? And like we did with the true error, we're going to define a relative approximate error. Because the approximate error in and of itself doesn't tell us how big the error is. It needs to be put in context. If you're doing iterations on a quantity where the order is 1,000 and you commit an error of 0.0012, that's insignificant. So you need to put that in context. However, if you commit an error of 0.0012 with calculations that are on the order of 10 to the minus 5, then that error is a very big deal. Why? Because relative to the quantity you're computing, 0.012 or whatever is a big proportion of that. So we define the relative approximate error either as the current approximation minus previous approximation over current approximation, or I like this definition a lot, the more accurate one minus the less accurate one over the more accurate approximation. Okay, and we typically put that under absolute value and multiply by 100%, so you report that as a percentage. My relative approximate error is 20%, okay, or 5%, right? Yes, supposedly, because, so what your colleague is saying, how can, is the current approximation, does that always mean that it's a better or more accurate approximation? Yes, most of the methods, all the methods that we study are what we call convergent methods. What that means, every time you add one more term to the approximation, or you do one more iteration, you're improving your guess, you're gaining more significant digits. And that means that the current calculation is better than the previous one. So 99% of the cases, the current approximation is better than the previous one. Okay, so it is more accurate. Okay, let's go on and do an activity. Don't mind the 2 minutes, probably take a little longer. You're going to do this by hand, like we did last time. So do it on your notepads or papers. Use your calculator. So here's what we're going to do. We're going to take the approximation to the first derivative, which we introduced last time, which is the rise over run definition that you learned in school. except we're not using a limit here. We're just using a finite value for this h. This is called the forward Euler finite difference approximation. We will learn that in a few chapters, but I want to introduce the name here in honor of Leonhard Euler. So this is called the forward Euler approximation for the first derivative. Okay, you know what f is. You're evaluating it at a given value of x. Then you independently choose the value of h, and you approximate the derivative at x using this formula. So all you need to know is f of x. You don't need to know f prime because you're approximating f prime. Okay. Now for the use this, take this and compute for the function f of x 2e to the 0.5x, find the approximate error in evaluating f prime of 3 using all of these values of h, 0.5, 0.25, 0.125, and 0.0625. Okay, so go ahead. The way I would do it, I would create a table. Okay, I would create a table. On the first column, I would put the value of h. On the second column, I would put my approximation, and on the third column, I would put my approximate relative error. Okay, so like this, something like this. Okay, h, f prime of 3, and the error. Okay, go ahead and try it for all of these values of h. So the first row is going to be at h 0.5. Compute that formula, use your calculator, use Python. Work in groups or individually. And you are to calculate the relative approximate error. Okay? So the relative approximate error, let me put the definition here. Okay, this is the definition of the relative approximate error, remember? The more accurate approximation minus the less accurate one over the more accurate one. Now remember, however you twist this, notice that as h is going smaller, from what we know about derivatives, about this definition from high school, is that the approximation is going to be better, right? Because that definition of the derivative is in the limit as h approaches 0. So the smaller the h is, the better the approximation, right? So the approximation with 0.25 is a better one than the one with 0.5. And the one with 0.125 is better than the one than 0.25, okay? You can do that as the most accurate calculation. That's a great point, but do it sequentially, okay? Do it sequentially. There's a point that needs to be made here because we want to see a pattern. We want to try to detect a pattern. If you cut h by half, what happens to the error? Okay, so that's what I'm after. But you're not wrong if you do that, okay? You're not wrong if you do that. But compare the current approximation to the previous one. In other words, compare the error committed from when computing with 0.25 to the one with 0.5. And then the one with 0.25 to the one with 0.25 and so on, okay? But you're not wrong if you did that, okay? Yeah. Over here. This group has some killer calligraphy. Like, have you seen your calligraphic abilities here? This front row, not bad too, but have you seen these guys in the back? You had some. Yes.
So, for the previous approximation, are you talking about these?
Yes,
So
yes.
current would be like 5.09.
No. So that's the previous. This is the current. So this one minus this one over this one, and then this minus this over this, and then this minus that.
Absolute value.
Yes, take absolute value.
So in that case, would it matter too much if we did it the other way or against it?
No, the other no. But as long as you divide, as the denominator is the more accurate one. Sometimes people make mistake, and you don't use the more accurate one. It's not the end of the world, but it's a more consistent estimate. Okay? Yeah.
Do you do estimates like this on the type of functions where it bounces up?
You can. Yep. Yeah. Yep. Because you're fixing this at a point, but this is you're doing it at a one point. So the value at that point is not going to bounce around, right? Yeah. I want you to just exercise. Yep, you're just because these are the calculations you're going to do in the exam. Okay. All right. So halfway through. Are we halfway through? So now, as you look at the error, okay, if you're done, I want you to think about what is happening to the error as we are reducing h. Okay? So in that table, you write the error. I want you to think about what happens as you reduce h. Okay? You guys are having trouble working on the exam. I'm just joking. I know some of you are doing it in Python. That's fine. But I'd like you to try to exercise your hands because this is the, well, get some rehearsal in doing these kinds of calculations because these are the calculations that you will see in an exam, okay? So if you didn't do it by hand here, just do it by hand at home, okay? All right. Let's see. What do you think about the error? What's happening to the error as h is reduced? Because that's what I want to learn from this lesson. What did you say?
It's halving.
It's halving. So what's your group's name? Did you come up with a group name? The Cowboys. Okay. So the Cowboys here are saying that the error is halving. So how would you phrase this statement? When we go from h.5 to 0.25, what's happening to h? We're having h is cut in half, and so the Cowboys are saying the error is cut in half. Do we have any dissenting groups to this idea, or those who agree or disagree? Do you agree? You agree. Okay, what's your group's name? Josh from the undecided group, or they agree. Okay. Others, what do you think? Oh, let's talk about it. Does it even, did you even see any pattern at all in the error? So in your table, you should see as h being reduced and it's being cut in half, indeed. What's happening to the error? Is it doubling? Is it cut in half? Is random? What's going on? Yeah? Cut in half. Okay. Right. What's your group? Did you guys come up with a group name? Oh, in honor of Professor Jeff Silcox. I love it. We need to take a picture of this and send it to Professor Silcox. He just went on retirement. Okay. Well, I agree. I agree with that. Let's see how this came about. Okay. So I created a table. The first column is going to contain the values of h. The second column is going to contain the value of my approximation. And the third column is going to contain my relative approximate error. So for h equals 0.5, f prime of 3 using the forward Euler approximation is 5.09 up to 3 significant figures. There is no error here. I cannot define an error, okay, because I don't have any other value I can compare to, okay? So you could say either undefined or we don't know, okay? Now, for h equals 0.25, the approximate value is 4.77, and the calculation current approximation or more accurate approximation, supposedly minus the less accurate one over the more accurate one, and it's 6.66%. Okay? Let's see, is this what you got? Yeah. Okay. Then at 0.125, the error is 3.22. And then at 0.0625, the error is 1.59. Now notice I'm cutting h in half on purpose. Okay? Because I want to try to detect a pattern. I'm inputting a pattern, and I want to see if I'm going to detect a pattern. Okay? And indeed, I do detect a pattern. The error is almost cut in half. Okay? We will learn later that this is a first-order method, that the forward Euler is a first-order method. We will learn about other methods where if you cut h in half, the error is going to be cut by a factor of 4. Okay? Those are second-order methods. I'm just kind of trying to see these ideas here. Okay. One of your colleagues made a great point. And Miles said that, well, what if in all of these, question there? No. Okay. In all of these, the most accurate approximation is the one with 0.0625. Agreed? Because that is the smallest value in this entire set. And we know that that derivative approximation is going to be the most accurate for that. So why not use that as the most accurate approximation? You will not be wrong if you do that. In practice, you will not be wrong. Indeed, this is the most accurate one. You can put the value, this 4.55, over here everywhere as the most accurate one, okay, in the denominator. It'll be fine. However, you won't be able to detect this pattern that I'm showing. Here, we're not only just studying a numerical formula for the sake of computing a formula, we're also trying to gain some insight into those formulas, how they behave. So on purpose, I needed to cut h in half to see how the error is changing. Once we observe that, we agree that that's the case, then you can then use the most accurate value or approximation to do your evaluation. Okay? Yes?
You said this method here is called a first-order approximation?
It's called the first-order approximation. We will learn that in a few chapters. Oh, yeah. Okay. So now you're going to repeat this in Python. Okay? So get your Jupyter notebooks up and running. Okay? Start a new Jupyter notebook. If you don't even know where to start, that's fine. Just try to put something. Even write pseudocode. Tell me what you think you want to do. Just write something. Okay? Working groups. You could have one terminal. All of you kind of hanging around the terminal looking. But I want you to try to think about how you would do this in a Python code. Okay? A brute force approach, quick approach, whatever. Okay? Now you're going to do it for all of these values of h. 8, 4, 2, 1, etc., etc. Okay?
Oh, that's what I did. I'm so good at this. Well, I saw it.
So let me see, Miles, what did you do? Show me.
I started by writing a function for the actual. I need to edit this to further use that table, but I just wrote a function to return a.
Yeah. Okay, so now, yeah. Okay, 3. Okay, so now you need to do it for all values of h. Okay? Yeah. Just try to write something. Try to write something. Yeah. Yes. 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 Yeah. So here's a little tip when you're thinking about designing your code. First thing you need to ask yourself is restate what you are being asked to do. Okay, so here we want to our objective is to calculate the approximate relative error when computing using the forward Euler formula to approximate a derivative. The key in all of this is this formula. So in the least, we need a routine, a Python routine, that computes the forward Euler formula. Now, what does that routine need to take as input? And what is it going to produce as output? That's up to you to decide, okay? If you have fixed the input function, the exponential 2e to the 0.5x, and if you fix the value of x, then all that routine needs to take is the value of h. And then you consistently pass that value of h to that routine. It's going to return a derivative. You take that derivative and subtract it from the derivative computed with another value of h, and you get an error. Okay, that's kind of the simplest way how you do this. So we're going to do it that way first, and then we're going to take it up a notch. Okay, so we'll start with that. Take a shot at it. Try it out. I am happy to help. If you, I can turn around and I can chat with you about the code. Okay, this is your time. Would you mind increasing the brightness a little bit? All right, thank you.
So basically, I'm making
An array.
with h, and I was trying to put in that array straight into the
Yeah.
print h. And if I do that,
It's going to give you an error.
probably
Yep. Run it.
because
Yeah. Yeah. So you're committing two errors here. The first one, this is a list. This is not going to be conducive to numerical computing because Python lists are assumed to be mixed lists. You can put numbers and strings and other objects in
Should I do a
that.
NumPy
So
array
you need a
instead?
NumPy array, exactly.
Okay, I already have imported NumPy.
Okay, so just do, np.array and parentheses, put the list in it, okay? Okay.
I don't need
No, just paste it. Did you copy? Did you
I
cut
did
it? Okay. And you still need the square brackets around it.
around.
Yeah, around those numbers. Yep. Open bracket and close bracket. Now you can't use the math module with NumPy. You need np.exponential. Okay. Yep.
NP, other than being different modules, np.ext and map.ext do the same thing.
Yep. Absolutely. But NumPy has vectorized operations. Okay. So it allows you to do calculations just one shot. There you go. Okay. So now I want you to do it for an arbitrary function.
Arbitrary function?
Wait, what is that? What if I want you to calculate the error for log sine x?
Oh, use a different function. I can do it. I see it change the.
What if I don't want to change that much? I just want to use it as an input. So your function needs to be as an input argument. Your function needs to be an input. Okay. Anyway, but this is good. Okay, this is good. This solves this problem indeed. Yes. Guys, you can use us, and the TAs are here if you want help. Yeah.
So I'm getting
We can just check with a calculator.
Yeah. What's up?
So I have my function written. So that if that's wrong, I can tweak it. But I'm mainly more concerned about returning the function and getting different values in here. So for my h, I used 8, and for my f, I used 3. I believe it was 3.
For x, you use 3. Yeah. So that's correct. That's what we want to tell you. But this is giving you only one value of the derivative. So now you need to repeat it. You either want a loop, you either want to do it over a loop, or
Is there a loop that I can write down just half h every single time?
You can do that, or you can put it in as an array like that. Yeah. But yeah, you can create. We'll learn about those things as we go. But yep, this is how I would do it right now. Okay. You got it. Okay. Okay. You got it? Yeah. Oh, wow. Yeah, you're like, okay. You could help me. Now plot on a log if you want. Yeah, so do it on a log plot. Okay? So, so plt.log. Just, and see what you should get a straight line. Ah. Almost a straight line. Are you cutting h in half?
No, I don't think I have the right values in there right now.
Okay. Good work. How we doing, guys? Talk to each other. I'm glad you're trying. Okay? That's your first this might be your first exposure to Python. I'm glad you're trying. Don't be frustrated. Okay. Should we do it together? Yes. Jeff.
For some reason it wants to now think that f is needing definition even though this is supposed to be equal to this. This is the new name.
But what is f? You're making a function called f of x plus h. What is f? You never defined it anywhere, right?
Well, I mean, not
What is f?
yet, I guess. I don't know.
Yeah, you haven't defined functions. You defined just a value over here.
I thought that's what I was doing there.
No, but f here is something. This is undefined, and you thought you were doing this here, but this is not a function. This is simply a value. Okay, you need to define a Python function for your 2.5 e to the 2 e to the 0.5x. Okay? This is not a function, this is a value. Okay? This is just a value, right? So it needs to be a function. It needs to be a Python function. Okay, I'll show you in a second. Okay. It can. All right, guys. Yeah, let's do it together. Okay, shall we do it together? All right, I'm going to switch to my Python notebook. Let me see. All right, so let's see. Window, move to built-in retina. Okay, I'm going to quit this one. And Jupyter notebook. Right. Okay. All right. Let me know in the back if you. Let's see. Okay. Let me know in the back if you can see this. Okay. All right. Let's focus together, please. All right. So first thing I do is put my name and what this homework is supposed to be or what this work is supposed to be. But I'm not going to do that in the interest of time. But I'm telling you, you should do that. Okay. All right. First, I always import what I call my boilerplate necessities, okay, the bare necessities, okay. Those are going to evolve with us over time, okay, and then we're going to settle in a few lectures. We're going to have like 4 or 5 libraries that we always import that are going to satisfy all our numerical methods needs. But for now, I want to import, most important library is NumPy. Import NumPy as MP, okay. Now that means I'm calling the NumPy library and I'm giving it an alias called np so that I don't have to call numpy.exponential or numpy.this or .that every time I need it. Okay, so I can just call np.something. Okay? All right, so that's the first thing I want to obtain. Now, when we look at the slides, we were supposed to compute the derivative for this function f of x. Okay, so I need a routine that computes the derivative. That's the simplest way I would think about it, right? So I'm going to create a Python function called df. So I'm going to do def, okay? I'm going to leave this open for a minute, and then I'm going to return some result, okay? Now, why did I do this? Because I want you to see how I actually think when I'm writing code, okay? I first spend an hour to pick a function name. After that hour, I have a beautiful function name, in this case df, like derivative, right? If it's a second derivative, it's going to be d2f, etc. So df, and then I open parentheses because every Python routine could take some arguments, okay? Or could take no arguments at all. In this case right now, let's say that the function you're computing the derivative for is fixed, okay? It's going to be 2e to the 2e to the 0.5x, so we know that. So that's a global function, okay? We don't have to bring it in as an input to this function, okay? So the only other arguments that I would need to evaluate to do the forward Euler method are x, the location at which we're evaluating the derivative. In this case, it's 3, but it could be another number. So why not just add it as an input argument, okay? So we're going to put x over here and h. Ooh, fancy. Right, it's nothing. We don't know what x and h are. That's the beauty of it. Those are going to be determined when we call the function. This function doesn't do anything until we execute it, okay? Now, my result is going to be f of x plus h minus f of x, okay, indeed, just like the formula, okay, over h. All right. So from the arguments, we have x and h, but we do not have f, okay? And we said that f is going to be defined outside this function, is going to be given. So we need a definition for f. And that f cannot be a value, it needs to be a function. Why does it need to be a function? Because I'm calling it here. Whenever you see parentheses, that 100% of the time, that is a function Python routine that is being called, okay? So when we call df, it's going to go in result and say, I'm going to call next f of x plus h. Where is f? If I can't find it, it's going to throw an error, okay? So I'll show you. If I call df at 3 and 0.5, it's going to throw an error. Name f is not defined, okay? So you could say, well, let's define f. You could say f is equal to 2.0 times np.exponential of, 0.5 times x, right? Okay, now x is not defined. Okay, so now let's define x. We got entangled into a mess now, okay? We got entangled into a mess. So I defined x now. Okay, f is defined now, but still it's throwing me an error. It's telling me here that numpy.float64 object is not callable. What that means is that I used something that I cannot call. And that thing, over experience, you're going to know that that thing is f of x plus h. Because the f, the way I defined f, is a value. I didn't define it as a function. So I need to define it as a function. Okay? And that's very simple. Look at that. I'm going to remove the sin over here. I'm going to do define f of x. I'm going to tell it return 2e to the 0.5x. Okay? So that defines f of x as a callable function. So we can evaluate f of x in its own merit, right? And df is the routine that calls that f and computes the derivative. So now all should be well with the world. There you go. df, the derivative with h equals 0.5 and x equals 3 was 5.09, okay? Just like we had in our table. Now I have confidence in this answer because I did it by hand over there. Why you need to check that? What if you missed one of the parentheses over here? You're going to get a different answer. So you better check. You better do it by hand first and validate with an answer that you computed by hand, okay? Okay. Okay, so now we have the ingredients necessary to evaluate the derivative. So now we have our second column, right? We can compute our second column in that table we created. Now we want away from that second column to be able, we want away from these values to be able to kind of take the difference between each other, right? Take the difference so that we can see how the error is changing. You could do a brute force approach. You could say for h1 equal 8, you could say df1 equal df at, so let's define x. This is the brute force approach, okay? Let's call this the brute force approach. And it's okay, you know, you're starting to learn programming. That's fine, do that. Brute force approach is we're going to call this function over and over and over again for every value of h, okay? It's going to take a while. I'm going to do it for 2 values of h. I'm going to tell you, you do the rest. And wait until I give you 1,000 values of h. That's going to take a lot of time. And that's, I'll make the point in a minute, okay? Okay, so then you could say my derivative with this value of h and x, so x is fixed at 3, h1, okay? h1, and then we have h2 equal 4. I'm going to put the decimal points to tell Python to treat those as floats. And this is the second value in the column at x, h2, okay? And then I could say, well, you know, my error 1 is absolute value of df2 minus df1 over df2, right? Times 100, and then, whoops, print E1. Whoa, 319%. That's bad error. We know that because the values of h are huge. But imagine now doing that for 10 values of h. While it works, but that's an ineffective use of a powerful programming language. What I did here is I used Python as a calculator, not as a programming tool. A programming tool should allow you to use smart syntax to compute things really quickly. Okay? To compute things really quickly. Okay. So a better approach, and not the only one. So I walked around. Some of you have phenomenal code that I couldn't even write. And great, but you know, again, the point is not to write Shakespearean code. The point is to just get enough exposure to coding so that you can write effective code. Okay, so how would we do this in another way? I'm going to teach you a concept called vectorized operations in Python. That's why Python is so beautiful, because it allows you to do operations on arrays one element at a time by just adding 2 arrays to each other or multiplying them to each other without having to do even for loops. So I claim that I can solve this problem without a single for loop. Okay, I'm going to show you that, right? First, I'm going to put a title, a slightly better approach. Okay, so best is the enemy of the better. Okay. Always aim to be better than you can, okay? Because the best sometimes is the point of diminishing returns. Well, that's at least what I try to do. Okay, a slightly better approach. First, I'm going to declare my h values. I'm going to call them h values, okay? And I'm going to create that as an array, okay? So what does this mean? You might have heard of the word NumPy array. If you haven't, now you're going to hear about it. NumPy is a numerical library, numerical Python, okay, that allows you to do amazing operations on numbers. And those numbers are typically stored in arrays. Arrays are nothing but a list of things. Okay, specifically for NumPy, they are just a list of numbers. MATLAB stands for Matrix Laboratory. MATLAB was so powerful and beautiful because it allowed you to do operations with matrices and vectors. Python is no different, okay? And it's as powerful, even more, okay? So here's what we're going to do. We're going to create an NumPy array with the values that we had for h, and I'm going to hard code them over here. Later, we will learn how to also auto-generate those numbers, okay? Because there's a pattern. I'm going to put 8, 4, 2, 1, 0.5, 0.25, 0.125, 0.0625, correct? Okay. So now those are the values of h, okay? Great. How can I make sure that I got them right? Okay, Nicholas and Brooke, what did I always say? If you are in doubt, print it out. If you are in doubt, print it out. There's no mystery here or magic. You want to know what you're doing? You want to know if it's working? Just print it. Print it. If you're in doubt, print it out. Always, okay? That's going to be an exam question, actually. If it actually was one of the exam questions. Okay? Okay, so print h values. Look at that. Yeah, Python indeed told me, yeah, my h values are 8, 4, 2, 1, 0.5, etc. Okay, great. On to the next step. Now, I claim that because everywhere I used NumPy, that if I call that, okay, let me not make that claim. Let's just ask a question. What happens now if I call this function with that NumPy array? What do you think is going to happen? Why not? This is exciting. We're going to have two camps. Kenna? Yeah? Okay.
Oh, no, it's going to, oh, it's in what,
Yeah. You did that.
It's going to pass the function
On every single operator. I think the same. Okay, so who agrees, who disagrees? I'm not trying to vet you against each other, but I'm like, I want to gauge kind of where we're at. I mean, it is surprising that, yeah, you're right. You might be inclined to say it's not going to work because this is an array and we defined the function f to take only one value of h. But that's the power of Python, is that if we pass an array for any one of those arguments, okay, and as long as we didn't commit anything that violates array or vector operations, if you bring in a single value, you're going to get a single value. If you bring in an array, you're going to get an array. So when we pass an array value of h into this function, it's going to go over each value in that array and calculate the function and return a result. You don't believe me? That's right. Okay, type with me. Okay, so let's, I'm going to delete those here, brute force approach, etc. Okay. Print h values. So let's call df at the value of 3 with h values. Look at that. In one shot, we were able to compute that entire column, the second column, in our table in the slides, correct? That's a vectorized operation. In that function up there, although I didn't make any assumptions on f and x and h, I didn't also make any assumptions that are going to break an array operation. And Python was designed, hey, you give me an array, you give me a matrix, I'm going to apply that function over the matrix. It's pretty powerful that way. So now we have our second column. Agreed? We have our second column that contains the derivative values. So let's store that in a variable. What do we kind of call it? df values, or df values, right? So df values, what is it? It's an array of derivative values. Print df values. Okay. It contains the values of the approximation of the derivative 2e to the 0.5x at x equal 3. Okay. This one corresponds to the value with h equal 8. It's horrible value, horrible result. 14, 7, 5, we're getting close, right? And you see, as h gets smaller, this is with h 0.125, and this is with h 0.0625. 0.0625. You don't believe me? Let's do it. I'm going to call df at point 3 with h 0.0625. Right? Okay. Okay. All right. Now, to the next step. I want the last column. Okay? And I don't want to do any for loop. I just want to reuse this array, df values. Okay? Now notice in our definition of the error, we want to take this value minus that value over this value, and then this value minus that value over this value, right? And then this value minus that value over this value, okay? And then the last one is going to be this minus this value over this value.
You said no for loops.
No for loops, yeah? No while loop, not even a while loop. What if we had two subarrays? One array that contains 60, 14, 7.7, 5.8, 5.0, 4.7, 4.6. So from the beginning to this one. And another array that contained the values that come next. Okay, so what if we had two arrays? Okay, one of them contained the first value all the way to the one but last, and another array that contained the second value all the way to the end, and we subtract them from each other. Isn't that going to give us the error? Yeah. Now, how do we get those arrays? Very simple trick. All NumPy arrays can be accessed by an index. To call a function, you put parentheses, right, in Python and in MATLAB and all programming languages. Now, to access a value inside an array, you access it with a square bracket and put an index. Okay? So, for example, if I want to access the first value in df values, I put df values 0. That's the first value. Okay? Agreed? Everything is indexed from 0. So when I say the first value, that's the first entry at index 0. The second entry is going to be at index 1. Agreed? Okay, at index 1. And so on, all the way to the last value. Oh, wait, what is the last value? Is it at 8? No, there's only 8 values, so the last index is 7. But how do you know that? How do I access the last value? You print it. If you're in that, you print it out. But also, take an array now. Yes?
You have an index that's 0, so what may not be values in the array, you have 0 through 7 for your.
You're correct, but what if I don't know, I forgot that it's 7 values, right? Yes, you can get the length of it.
You use -1.
Okay, why?
You put negative counts from the back.
Okay, so think of arrays rather than thinking of them as a line, think of them, just wrap that line around. You can go through that line clockwise or counterclockwise. So you can index 0, 1, 2, 3, 4, 5, 6, 7, or you can index -1, -2, -3, -4, -5, right? Okay, let's do that. Oh, look at that. df values -1, it started counting from the end. So now it's going backwards. Arrays, put them on a circle. NumPy arrays, put them on a circle. You can index clockwise or counterclockwise. Okay? So now, -1 starts giving me the last value without even knowing the size of the array. I don't want to add one more line of code to count the number of elements in the array. Obviously, as you go through -2, it's going to give you the 1 second from last. Okay, there's one more trick to Python indexing. if I go, turns out that with Python arrays, with NumPy arrays, you can take out a chunk of the array by using a semicolon. So you put a semicolon here. On the left, you tell it which value you want to be first. And on the right, you tell it which value you want to be last. So if I go from 0 to -1, it's going to give me the same entire array, except for, so it goes from 0 to this number -1. Okay, so it went to this guy. Okay? So let's say you want to take the first 3 entries. So you want this and this and this as a subarray. Okay? You go from 0 to 3. Or you can go from 1 to 3. Okay? Indexing. However you want to use those numbers. Sometimes they might not make sense, gives you an error, then, oh yeah, I made a mistake in my indexing. You're worried, you're confused about it, you forgot it. Create a 5-element array and remind yourself. And always, if in doubt, print it out. Okay? Yes? It's still a NumPy array, absolutely.
So why is it only printing out 3 values? You went from 0
To 3 because it's indexing 0, 1, 2.
Oh, it's not.
Yeah, it's not inclusive. Yeah, it's not that. It's an open bracket at the end. Okay. All right. So here's how I'm going to get my 2 arrays. df1 is going to be this guy, and the other one is going to be df values. Remember, we said we're going to take from 0 to this guy, and then from 1 to that guy. How do I access that guy? I'm going to go from 1 to, I'm not going to put anything over there. I'm not going to put anything. It's going to give me all the way to the end of the array. So let me print it out. So print df1. Indeed, it gave me 60, 14, 7, 5, etc., all the way to this one, which is the first set of elements we wanted. The second one, df2, let's see what it does. Look at that. Gave me 14, 7.75, all the way to 552. So now if I take the difference between the two and divide by df2, multiply by 100, that's going to give me an array of errors. Not one, an array of errors, all of the errors. Okay, so let me do that. Error is equal to absolute value of df2 minus df1, over df2 times 100. Oh my gosh, is it going to work? Yes! That. Isn't this cool? Not a single for loop. Clear, simple, yes?
Isn't Python basically just running a for loop?
It is, yeah, and it's more effective though. It's much better than the for loop that I or anyone else is going to write because it's indexing at machine language level. It's way faster. But you're right. What Python did here is it looped over df1 and df2. Okay, it looped over each element. Took the first entry in df2 minus the first entry on df1 over the first entry in df2. Go compare it to what we did by hand. These are the numbers we got by hand. 6.66, right? 3.22 and 1.59. That's what we got when we did it by hand, right? This is correct. Okay, so now let me delete all the lines that we didn't need. Okay. I mean, you want to show off your code a little bit, right? It's like 5 lines of code to do the whole thing, right? And look at that. It's great. You're ready for more? Awesome. Okay, how about we take 5? All right, let's get back. Okay, so now the next question, let me see, is also going to be a programming question. Now, repeat the previous coding activity, except now we need to be able to do it for an arbitrary function. Again, we need to be able to use our routines so that they're useful, right? If you give the code that only approximates the derivative for 2e to the 0.5x, and every time I want to make a change, you have to pull up your code and rewrite everything, right? That kind of tends to defeat the purpose. It's going to take us 1 30-second interval to do, or 1 minute to do this change because of the way we set up the code. So I'm going to go back to Python, to the Jupyter Notebook, okay? Now note how we defined f of x as its own function, but in the derivative definition, the routine, so let me distinguish between function and routine. Let's agree to call Python definitions, Python functions, let's just call them routines. And we'll reserve the word function to math, okay? So correct me when I make that mistake, please, okay? It's very easy to make that mistake. So this Python routine that computes df, currently, it takes x and h as input values, but nothing prevents it from taking a function as an input, right? Nothing prevents it from taking a function as an input. Now, if you've done C++, that's a nightmare because you cannot pass the name of a function as a part of your arguments. But in Python, it's like, yay, everything is going to be allowed, okay? And they allow that, which is fantastic, right? So I'm going to pass one more argument to this function, to this routine, df. I'm going to call it f. I'm not going to change a thing, okay? I don't need to change a thing. So now I'm going to define another function, another routine called, Tony's function. And I'm going to return, 2 times mp.sign, mp.log x. Okay? Now, all of this can be done on, okay? Now, my df, I'm going to call it on Tony's function. It's going to work. It's just going to evaluate the derivative on Tony's function. Okay? I'm going to pass that as an argument. Look at that. It computed an error, and it's just completely fine. If I give it back our original function, let's call it my first function, okay? And if I do my first function, it's just going to work. Pop, pop. That's it. Very simple. If you had hard-coded 2e to the 0.5x, you're not wrong. You got the answer right. And I'm really not going to care if you do that in your homework, okay? That's absolutely fine, and it works. And in your codes, it works. I'm just showing you, you might want to make it a little bit more general, but be careful. Sometimes in our pursuit of being very general, we obfuscate the purpose. We add so many knobs and buttons that the code becomes useless. Okay, it's like when you get a software upgrade and they add like 100 features. I'm like, I just want to, export a file or just save it, right? Why do you have to add 2,000 features? Okay, so just be careful. It's a balance between how general you want your code to be and how specific it is, okay, to accomplish a purpose. Okay? All right, we have a few more minutes. Okay? And I was going to go through a discussion on another example, which we're going to do by hand, and then we're going to call it a day, okay? Okay. Another example of approximate error. And that's a little different than what we did so far, where we just had one formula, one approximation, which was the forward Euler. And we knew with certain values of h, we had a better approximation than with other values of h. Now what I'm going to present now is a formula to calculate functions and other things as well, based on what we call the Taylor series, which I guess you've seen or you've heard of. We'll have a chance to dig a little bit deeper into Taylor series. However, the Taylor series is a great example of a formula, numerical formula, where you have to add more and more and more and more terms to get more and more accuracy. Okay? For example, the sine function, when you punch in sine 0.375 in your calculator doesn't know how to compute sine x. There's no like, sine x is just a symbol for the sine function. But to calculate the sine function, all of the routines you see in math, Python, and NumPy, and MATLAB, in your calculator, they actually execute a Taylor series, what we call a Taylor series, to approximate that function, to get a value of it. Turns out that all continuous functions can be represented as polynomials. That's what the Taylor series is. That's what it tells you. We can represent all functions, all continuous real functions, as Taylor series, or as an infinite polynomial. For sine x, you have this polynomial, x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on and so forth. For the exponential function, it's a different polynomial. It's 1 plus x squared over 2, etc. For other functions, it's other polynomials. Now, this equal sign is equal. It's not an approximation because I'm adding all the terms to infinity. But your calculator, my Python, your friend's MATLAB does not have the capacity to calculate an infinite series. So we typically stop after a certain number of terms. Okay? We stop. We say, well, you know what? We're going to do 5 terms. We're going to do 7 terms. How do you choose? We'll discuss. We'll learn that on Thursday, how many terms you need. But suppose you're adding terms. Clearly, if you can approximate the function sine x with the first term, so sine 0.5 would be 0.5 as the first term. Or you can add 2 terms, 0.5 minus 0.5 cubed over 3 factorial. Or you can add more terms. Now what that means, the more terms you add, you have a current approximation or a more accurate approximation. Which means with every term you add, you can also define an approximate error. Okay? And that's what you're going to do in this next activity. You're going to evaluate the Taylor series for the exponential. Okay? This is the Taylor series for the exponential. You're going to do it for 1, 2, 3, and 4 terms at x equal 2. So you're going to evaluate it. You're going to evaluate e squared, okay, using 1 term, using 2 terms, using 3 terms, and using 4 terms, and you're going to compute the relative approximate error. So again, do the same table: number of terms, value, and error. Okay. In the previous table, we had h, value, and error. Now you have number of terms, value, and error. Okay. So like this, number of terms, okay, like the first term, you add the first term, so on, you have a result and you have an error. Okay? Yeah. Yeah, x equal 2. Yeah, so e squared. So you're doing e squared using this approximation. Okay? Using the Taylor series, but we're gonna cut it at first time 1 term, 2 terms, 3 terms, and then 4 terms. And with every time you add a term, you are able to evaluate the error you're committing, the relative approximate error. Okay? This activity needs to be mechanistic, okay, because it's very prone to committing mistakes. But these are the types of calculations you're going to be doing in exams, okay? Okay, there's 1 more minute. So I'll show you the first 2. So if you add 1, if you have 1 term, your approximation is 1, and we don't have any error defined. But if you have 2 terms, it's 1 plus x, so it's going to be 1 plus 2. Your result is 3, and your relative error is going to be 3, current approximation minus previous approximation over current approximation, and 66.7%, right? And then you add 1 more term, so you have 3 terms. If you have 3 terms, your result is your approximation of e squared is going to be 5. The error committed in using 3 terms is 5 minus 3 over 5. That's the approximate error. It's 40%. Okay? Then you keep adding terms. Okay? Please repeat this exercise by hand at home. These are the types of problems you will get on exams and homework. Okay, homework is going to be mostly focused on doing it in Python. All right. Well, thank you.